Welcome. We are from Allen High School and we are pre-AP chemistry level, and we are going to be looking at the heart of chemistry, which is the mole, and trying to understand what scientists mean when they use that. And no, it's not a little furry animal. I hope you appreciated the comics about that at the front of your notes. We are on page 3, at the top of page 3 of your notes, so let's forge ahead. Now, I want us to do a thought experiment. We talked about atomic mass units, but we can't really visualize atoms. We can't measure atoms. So, let's take something like sulfur. If I took 32.07, remember that was its atomic mass unit. And if I measure that exact number in grams, all right, just numerically equivalent. These are atoms, and this is much, much larger, but just the numerical equivalent. If I counted all of the atoms of sulfur in there, I would get 6.02 or 022, however many places you want to take it out to, times 10 to the 23rd atoms. Now, it would take me 1.91 times 10 to the 16th years, apparently, but still, it's a thought experiment, all right? Now, let's do something similar with a metal. What if I took strontium? Well, its atomic mass units is 8.7 or 87.62 atomic mass units. So if I took that atomic level weighted average of protons plus neutrons, and I weighed out the numerical equivalent of that in grams, and then counted 1.91 times 10 to the 16 years later, I would find out I have 6.02 times 10 to the 23rd atoms. Not sure if you're noticing a little pattern yet, but let's see. What if I took a molecule? Let's start with something simple. So let's start with water. All right, water, remember, was 18.02 atomic mass units. Now, if I took that numerical equivalence, went to the balance, and weighed out the numerical equivalence in grams, and then counted 1.91 times 10 to the 16th years later, I'd found that I'd have 6.02 times 10 to the 23rd molecules. All right, you might not be convinced yet, so let's do something more complicated. Sugar. One of sugars, this could be, glucose, fructose, there's a variety of things, C6H12O6, right? And if that has an atomic mass unit of 180.16 AMUs, if I took the numerical equivalent of that in grams and counted it, I would get 6.02 times 10 to the 23rd molecules. All right, now just for grins, let's do a formula unit. There's one down a little further in your notes. So if I took sodium chloride and I added up one sodium plus one chlorine, I would get 58.45 atomic mass units. And again, if I took that number and made it grams instead, now I'd have grams. If I counted, I'd have 6.02 times 10 to the 23rd formula units. All right, it doesn't matter whether I'm counting atoms or molecules or formula units. I get the same number. So just like a dozen, right? 1 dozen is equal to, of anything, is equal to 12. And I'm not talking about a baker's dozen. So of that, so if it's a dozen cookies, then I have 12 cookies. If it's a dozen students, then I have 12 students. I think you get the idea. If I have a dozen desks, I have 12 desks. A dozen simply means 12 of what we're counting. And that's what we have here. This number here was determined not by counting, but by a dead guy named Avogadro. So this is Avogadro's number. And we're going to use it when we are counting. So I like to do count, Avogadro's number. When you're counting, we use Avogadro's number. And we call that 1 mole. And so 1 mole is equal to 6.02 times 10 to the 23rd of anything. Grains of sand, pennies, blood cells, and there's a whole list of analogies on your notes that's very interesting. One I heard is that a mole of sand would cover the city of Los Angeles to a 1-mile depth. So I don't know what year that was or how big Los Angeles was, but I think you get the idea. It's an awful lot of grains of sand. And since we have that equality, we have a conversion factor. And so you guessed it, we're about to do dun, 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 dimensional analysis, just like we did back at the beginning of the semester. And you actually used this conversion factor. You didn't really understand it, but you used it. So count Avogadro's number. We're only going to use Avogadro's number when we're counting. We're not going to skip from moles to grams, right? So here's what the size of a mole is. Watermelon seeds is bigger than the moon, or pennies, 7 stacks to the moon. I think you get the idea. It's a lot. And yet, if we're dealing with something teeny, teeny, tiny like a molecule, a 5-pound bag is 6.6 moles. So it depends on the size of what you're counting. So we're going to be using these numbers as conversion factors. So if we had carbonate, calcium carbonate, what we say is if we added the calcium, the carbon, and the 3 oxygens, we would have 100.01 grams equal to every 1 mole, which we've now discovered is 6.02 times 10 to the 23rd formula units. Now, we're not going to skip from here to here. Some teachers teach that. I don't. I find we flip-flop conversion factors if we do. So we're always going to go through this heart of chemistry. And when we're going from the mole to counting, we'll use count Avogadro's number. When we're going from moles to mass, we are now going to call this the molar mass, the mass of 1 mole. And we get those values from the periodic table. So we're going to want to do quite a bit of mapping out of this. So you have 200 grams. Let's go ahead and put a decimal point there. You know how I hate single sig fig numbers. So we've got 200 grams of calcium carbonate. And we want to know in the question, how many moles is this? Well, if each mole is 100 grams, we've got about twice that, right? So we should get 2 moles. But let me show you how we would set that up with dimensional analysis. You take your starting number. Remember, we used to start opposite the question mark. Grams of calcium carbonate. Now, I want to do a dimensional analysis. I'll do this first one using those the parenthesis method, and another one I'll do the railroad method. You can use what you want, but you must use dimensional analysis on this. All right, so let's take a look. I've got grams in the numerator, and I want to eliminate them. So I'm going to put them in the denominator. And I want moles. Now notice what my molar mass says. That for every 1 mole, right, that's implied that many grams for 1 mole. So for every 1 mole, I have 100.01 grams. And sure enough, I get 2 moles. Okay, let's try another one. So I have 63.2 grams, and I want to know how many moles this is. Now, you might want to ask yourself, are you counting? If you're counting, we can use Avogadro's number, and we're not, so we can't. Your temptation is going to be to use it all the time. Remember, we go grams to moles, the heart of chemistry, and then, in this case, it's formula units. This is where we use count Avogadro's number. We're only doing this step right here. Okay? So I start with my given, 63.2 grams. I'll use the railroad method. Remember, we used to set it up this way. Put a line there and a line there. It's a single step, so I only need one. I have grams. I want to eliminate grams, so I'm going to put them there. And I want moles. Now, another way you can write this molar mass, which is the mass of 1 mole, atoms, formula units, molecules, doesn't matter, is that for every 100.01 gram, that's equivalent to 1 mole. Okay, when we have a slashed unit, we have a conversion factor. There's a 1 in front of the mole, and there's a 100.01 grams. So what that's saying is that for each substance, we have a unique conversion factor when we're dealing with mass to moles. So mass and moles use molar mass, and it's a unique molar mass for each substance. Now, if you did this algebra, I have 3 sig figs. Oh yes, you heard me, 3 significant figures. So my answer needs to be to 3 significant figures. Remember, when you do the railroad, you multiply if it's in the numerator, you divide if it's in the denominator. Whoops, messed up on that one. That should be moles. Sorry, it was wrong in the teacher notes, and I just followed. That's moles. Don't forget your units. On your free response, you will miss points for significant figures and units. You have to show me those. All right? Now, we have quite a bit more to do with that. That's introducing the molar mass and how we use it as a conversion factor. Now we're going to look at how we can use it as both a conversion factor and a formula. So we're going to go through a whole series of calculations in the next video. So until then, this is YBCT, your best chem teacher, signing off.